Yes, we are still very much at the network layer, but the good news is we are done with the majority of the functionality. We covered this, we covered this, we covered this. The only piece remaining is this. So in the next few videos, we will wrap up routing. In this video, I'm going to provide an overview of routing. The details will come later. But first, a few recap questions. So the role of the network layer is to forward a packet from a source host to a destination host. And as part of this forwarding, it looks at these forwarding tables. So how are these forwarding tables built? That is part of the routing protocols. So that's what we are focusing on currently. I mentioned this before, but let me emphasize again, there is a difference between routing and forwarding. The task of forwarding is to get a packet, look at the destination and decide on which output port at the given router this packet has to go. So for this, it consults a forwarding table. The task of routing is to build such forwarding tables. A terminology that we are going to use in the future is routing domain. Basically, all routers that fall under the same administrative control fall in the same routing domain. For example, routers within a university network like IITB fall within one administrative domain. Similarly, routers that belong to an ISP network fall under a different routing domain. So it's possible that you could employ different routing protocols in each of these routing domains. Routing depends heavily on graph theory. Here is a graph. So this graph has what are called nodes and edges between the nodes. These nodes are also called vertices. And an edge is often associated with a cost that is represented here. And if there is no edge between two nodes, like there is no edge between A and E, one can view it as an edge with infinite cost. So how does a graph relate to the networking domain? Basically, these nodes that are part of the graph could be either hosts, routers, or networks. So for now, we will view these nodes as routers, but later I will get into how things are done in practice. And these edges between the nodes actually correspond to the physical links. And these costs translate to the cost of moving a packet on this particular link. By the way, cost doesn't necessarily mean money here. It could capture the time it took for a packet to go from A to B. Another term that we will use is neighbors. So a node has certain neighbors, which are the nodes that are directly connected to this. So for example, the neighbors of node A are node B and C because it has direct links with them. So what is the goal of routing? Basically, it looks into finding the least cost path between two nodes. And the cost of a path is nothing but the sum of the costs of the individual edges. For example, if I'm trying to find a path between nodes A and E, if I look at this figure, here is one path. And this path has a cost 1 plus 9, that is equal to 10. Here is another path. And this path has 1 plus 3 plus 4 plus 2, this is also equal to 10. And there is another path like this. And the cost of this path is 11. So either of these two paths can be the least cost path. By the way, an assumption we make henceforth is this graph is undirected graph, where if I look at two nodes A and B with a link and it having a cost of 1 means it's the same cost if a packet went from A to B or a packet went from B to A. But there could be directed links, in which case the cost of going from A to B could be 1, but the cost of going from B to A could be 10. So in my explanations later, I will focus mostly on undirected graphs. So where were we? We were looking at finding the least cost path between two nodes. Often this problem is called the single pair shortest path problem. Often in routing, we are more interested in this particular problem, that is a single source shortest path problem. What this is you try to find the least cost path from a source to all the other nodes in the graph. Why do you think this is the focus in routing? Often when a packet comes to a router, this could be destined to any of the hosts that are being served by the individual routers. So you need to find the shortest path between this router to any of these other routers. And you want to do this in an efficient fashion. That is where the single source shortest path problem comes into play. So this is a very well studied problem in graph theory. If you have already done the subject, you would have come across Dijkstra's algorithm. But if you haven't done it, I would suggest that you read up on Dijkstra's algorithm. I will not get into the details of these algorithms as part of this course, but I will mention one principle that is employed by many of these routing protocols, that of the optimality principle. Suppose this is the least cost path between two nodes X and Z, and let's say Y is an intermediate node on that particular path. By the way, there are other nodes as well. I'm just focusing on one intermediate node Y. Given that this is the least cost path between X and Z, what can you tell about the path between Y and Z? It turns out that this is the least cost path between Y and Z. Why? If indeed this was not the least cost path, you could replace this path with this other least cost path, thereby being able to go from X to Z over a even lower cost path. So this violates this assumption that we made that this was the least cost path between X and Z. So basically, if an intermediate node Y is on the optimal path from X to Z, Y to Z is also an optimal path. Now, given this rule, answer this question for me. Suppose you have this network topology graph and I have identified one node, let me call this the destination node, and I'm going to mark on this graph the optimal paths from all these other nodes to this destination node. What will these marked up paths form? Well, basically they will form a sync tree rooted at the particular destination. Because you're trying to find out the shortest path, they will all form a tree to this particular destination, because as I mentioned, if this is on the shortest path, this also will be on the shortest path. So here are some features of this sync tree. One, it need not be unique. You can have multiple sync trees. Because it is a tree, there are no loops possible, which means that each packet can be delivered within finite hops. And another useful feature is for undirected links, a given source to all destinations also forms a tree. So this tree, you're trying to find out the shortest path from different source to this particular destination. But if you flip it where this becomes the source and you're trying to find out what is the shortest path to all these other nodes, because the graph is undirected, the same tree will work. So the goal of the routing algorithms is to help find such sync trees for all the routers. So I hope this makes it clear as to what we are trying to achieve as part of the routing algorithms. So that's theory. When you're implementing, you have to handle many other things, and there are quite a few approaches. So let's look at these approaches. So the first approach is whether you should go for a static or a dynamic implementation. So what do I mean by static? In static, I assume that the network topology, the costs are fixed. So the routes can be computed in advance and then can be downloaded in all the routers. Whereas a dynamic routing algorithm approach handles the changes in the topology. For example, nodes can fail. New nodes can be added to the particular topology, and the cost itself can vary over time. So if you had a static routing algorithm and a dynamic routing algorithm, which one would you prefer? Naturally dynamic, right? Because all these are facts of life. You have to handle these issues in reality. So dynamic is preferable to static. So the next question to implementation is whether one should go for a centralized approach where all the nodes pass their neighborhood information to a central node, whereby the central node now can determine the entire network topology, because each node tells who its neighbors are, and then the central node will calculate the routes and redistribute them to all the other nodes in the particular topology. In contrast to central, you could also do distributed, where each node determines the routes by itself by exchanging messages with its neighbors. So what is the problem with centralized approach? The problem with centralized approaches are that there is a single point of failure, which to some extent can be handled by backup nodes, but it also has scalability issues because all the routers are going to direct their traffic towards one central node, and that link can get congested. And it's not that distributed approaches are better. Distributed approaches generally tend to be a lot more complex than centralized approaches, but in this community, the distributed approaches are preferable to central because handling these both is more important than the complexity aspect. Yet another approach is global versus local information. In global information, each node determines the entire topology information and then calculates routes based on this. By the way, this is not centralized. This can still be distributed, where each node via appropriate message exchange can gather information about the entire topology and calculate the routes. In local information exchange, nodes do not have global information, but based on the message exchanges, they can still determine routes to the destination. Unless we cover specific algorithms, I think these aspects will not be clear, but the popular approaches in routing are, most of them are dynamic and distributed, and you have flavors of both global knowledge as well as local knowledge. In this course, we will look at link state algorithm that falls under this global knowledge paradigm and distance vector algorithm that falls under local knowledge. So when we are designing these routing protocols, naturally we want to find the optimal path between a given source to all the other destination nodes within the particular graph. What other features would you like your routing algorithm to have? Can you name at least two? There are actually quite a few features. The optimality is what I have mentioned so far, trying to determine the least cost path. Another important feature is also correctness. In other words, your algorithm should give an output when indeed the path actually exists. It shouldn't give a false path. Simplicity is very important when it comes to implementation. Routing link failures are very common, so the algorithm should be robust against these kind of failures. One very important criteria in routing algorithms is convergence time. So since you are trying to gather information about the network topology and determining routes, you should be able to converge quickly to the equilibrium whenever the state changes. By state change, I mean either a link failed or a node failed or some cost increased from that state to again determining whatever is the least cost path. The algorithm should quickly converge to the new equilibrium. And naturally, when you design these algorithms, you also want to maintain minimum overhead, by which I mean the number of messages you exchange to determine the routes as well as how often you exchange these messages. You want to keep it to a minimum. And you also want to be able to handle large number of nodes as part of your routing algorithm. By large number of nodes, I mean many routers that form the network topology. So before I conclude this video, let me touch upon this cost metric. This is the cost associated with a link. When I try to find the least cost path, this metric becomes very important. Suppose every link in the graph were assigned a cost equal to 1. What does the least cost path boil down to? Hop count, right? So what do you think of this metric? Is it a good metric? An exaggerated topology, but nonetheless it makes the point. Suppose this were the topology. Would you like your packets to go directly from A to B via this 10 kbps link, or would you like your packets to go this way via these 2 hops over 1 Gbps link? Had you used the cost equal to 1 for each of them, your packets actually would go over this extremely low bandwidth link, which is not desirable. So setting the cost equal to 1 is not a good metric. Basically, it doesn't distinguish between links based on bandwidth, not just bandwidth, delay, current load, losses, so on and so forth. In light of the above, can you think of a better metric? So looking at the example above, you might have thought, why not set the metric to 1 over link bandwidth? So if the bandwidth is very low, this cost will be very high, and vice versa. I am calling this a static metric because once the cable is laid out, the bandwidth does not change. So this metric also typically does not change over time. Do you see any issues with this particular metric? Look at this topology. Let's assume that the link bandwidths in this particular graph are all the same. In this case, the shortest path turns out to be this. Basically, it boils down into a hop count as a special case because all the link bandwidths are the same. Now, what if this link is extremely congested because there is a lot of traffic going in this direction? Would you still prefer this path? Probably not. You would now like to go to B via this path. Metrics that are function of traffic can no longer be static. So we have dynamic cost metrics. This can be captured via the queue length at that particular node or via the delay experienced by a packet when it goes over that particular link. So what do you think of these metrics? Do they have any issues? Have you ever been in a grocery store standing in a line when the line next to you seems to be moving faster? So you change your line and then the previous line starts to look more attractive. So grass always looks greener on the other side. So this problem is called the ping pong effect. Why is this happening? So for example, if you are dealing with queue length information, when the queue builds up, the traffic will now get directed to other paths. Now this queue has become small and thereby the cost is again going to drop. When the cost drops, the other traffic again starts coming to use this link. So this is the ping pong effect. So this does not lead to stability in the network. So many dynamic metrics suffer from this ping pong effect, leading to a lot of churn in the network. So people have experimented with some of these metrics in the internet, but of late the reality is that these links are assigned static cost by administrators. Often this is a function of the link bandwidth because stability is more important than perfect optimality. And this metric doesn't do too bad either. So here is a summary of what we have seen. Routing is based on graph theory, and the goal of routing is to find optimal path between the nodes. When it comes to implementation, there are quite a few approaches to routing: static versus dynamic, distributed versus centralized, so on and so forth. But the popular techniques that are employed are dynamic distributed based on either global or local information. Now that we have a good understanding of what is involved in routing, up ahead we will look at some popular routing algorithms.